Welcome to Algebra 3, Advanced Mathematics. We're in Lesson 29. We're going to talk about the unit circle. So the unit circle is a drawing, in previous years, it's a drawing that illustrates the 30 degree, 60 degree, 90 degree, and the 45 degree, 45, 90 degree reference triangles. Those two reference triangles that we use and positioned within each quadrant of the Cartesian coordinate system such that each leg, or such that the vector here is shown where each leg is 1 unit, I think. No, it's where you have 1 unit here, and you can position that triangle within to get that degree of measure. So your first one would be here. You have 30 degrees. I'm trying to, it's my mouse is really touchy. It's one of those touch mice with the Mac. So it's, there we go. That's pretty close. All right, so we're at 29. I wish I could type it in and show you. There it went. I almost had it. There it is. All right, at 30 degrees, I don't want to show the coordinates. At 30 degrees here, my hypotenuse is 1 unit away. The hypotenuse is always going to be 1 unit away because it is the vector for the unit circle. It's a 1 unit circle. So the hypotenuse is always equal to 1 regardless of where it is along the circle. Now, the adjacent side, that is the side that is adjacent to your triangle, and this is a really cool tool, by the way. I found this on GeoGebra.com. It is just Google unit circle and click the one on GeoGebra, and it will, geogebra.org, and it will take you to this page, and you can actually, play around with it, and it will help you find these units of measure. So in this unit circle, you don't have to have the drawing done for you or figured out. And basically lesson 29 is saying, hey, here's how you can, just how we learned how to figure out the sine and the cosine using our reference triangles. That's what it's trying to show us for the unit circle. It's how to treat that like a vector on our Cartesian coordinate system, but also it's trying to show us how to find the quadrantal angles as well. And a quadrantal angle is simply when our angle, our vector, is equal to the axis or an axis. So if you have this, all right, I'm going to have to move. All right, you have this angle here, and it's at 0 degrees. Let me get it down to 0 if it'll let me. It doesn't want to do 0, but the coordinate here is 0, 1, right? When you have it on the axis right here, what happens is you have a teeny little triangle that's squished way down. And you have to kind of envision where that triangle would be if it was pulled out a little bit. So if I pull it out a little bit, you can see that here's the angle, here's the opposite side, and this is going to be the adjacent side to the angle. The angle is always going to be near the origin, okay? So understanding that tells you that, the hypotenuse is always 1. But when it is on the axis, then the adjacent side is going to be equal to 1 when it is on the x-axis. The opposite side is going to be 0. This is the opposite here. And if it is across the x-axis on to this other side, on the negative side, that would be 90, 180 degrees. Then the opposite side is here. The angle is always near the origin, and the adjacent and the hypotenuse are equal, and they both have a unit of 1. Okay, So we can take those values that we get. Let's go back over here to our tablet. So if on the x-axis within the coordinate system, let me draw one here. When we have our angle, our vector is from here to here. This is the opposite, and the adjacent and the hypotenuse are basically the same line. Same thing this way. Our, that's right on top there. Our opposite is going to be here, and our adjacent and our hypotenuse is basically the same line. And that's when you have a 0 degree or a 180 degree vector. So finding the sine, the cosine, and tangent of those, these are both equal to 1, is a matter of just putting them in the system. Now this would be, the hypotenuse is always positive, so that means that your adjacent side would be -1, right? Think about that. Your adjacent side, it has to go with the positive, negative side here. So your adjacent side is going to be -1, and your hypotenuse, which is always positive, is going to be +1. So we can just fill that information in. The adjacent and the hypotenuse are both equal to 1 here. So I'm just going to put a comma between the two instead of writing it separately. But your opposite side is equal to 0. I'm going to put a line through there so you can see the difference. The opposite is equal to 0. So then when you want to fill out your sine and cosine, you know how to do that. So SOHCAHTOA, I don't know why I put an equal sign there. It should have just been a dash. SOHCAHTOA. So your sine, opposite over adjacent for 0, let's do the sine of 0 degrees. That would be the opposite over the hypotenuse, would be 0 over h. So then the sine of 0 degrees would be 0, right? Because, sorry, we know the value of h, that's 1, so it'd still be 0, even though we know the value of h. The cosine of 0 degrees would be the adjacent of 1 over the hypotenuse of 1, so the cosine would be 1. And your tangent of 0 degrees would be the opposite over the adjacent, so that would be 0 over 1, so that would be 0 also. So you see what we're doing here. We're figuring out, based on where the angle is, which axis it's on, what those values are in relationship to sine, cosine, and tangent. Now, when they're on the y-axis, we have a different scenario because the origin is still down here. But then that changes because we refer to everything, we refer our triangles back to the x-axis always. So now the adjacent side and the opposite side switch. So where before this angle here made this the adjacent side, we bring this up now. Well, I guess it's still the adjacent side, but the adjacent side switches from being a 1 to a 0. So you can see that. Now, the opposite, which is in blue, is here. And the adjacent, which is orange, is here. And the adjacent is 0. So that's going to be true for our 90-degree angle and our 270-degree angle. So let's go back in here and I'll show you that. I'm going to use a different color. I'll use black. So when our angle, our vector, lands on the 90-degree, I don't know why I did that. Let me put it right back where I want it. I want this one right here. There we go. So when our vector lands right on the positive y-axis, right? This is still the adjacent, but the adjacent now is equal to 0. And the opposite, because this is going to be the length here of the adjacent, the opposite is going to equal 1, and the hypotenuse is going to equal 1. And it's a positive 1 because it's straight up and down, right? But then when we go all the way around to this side here, again, the adjacent, it's at the origin, it's going to equal 0. But the opposite side, let me give myself a little bit of room, the opposite side is going to equal -1 because it's on the negative side of the axis, and the hypotenuse is going to be +1 because the hypotenuse is always positive. And then we can take these values here and these values here, and we can figure out sine, cosine, and tangent because of that, or based on that. So we just put them into our formula and solve for each one of those if we want to. Here's what you can do, which is much simpler. I want you to understand where your sine, cosine, and tangent come from, but there's absolutely no reason for you to frustrate yourself over it, right? Understand that this is what this means, but use your calculator when you need to. Don't kill your brain cells over trigonometry. It's not worth it. Instead, when you have a 180-degree vector, put in 180-degree sine. It's going to tell you it's 0. It's going to tell you it's 0, right? You can do that here, right? Or if you have, let's say this is the cosine and it's adjacent over hypotenuse. The cosine of, this is 180 degrees, is the adjacent over the hypotenuse, right? -1 over 1. Guess what the cosine of 180 is? -1. We figured it out here. We can do it, but we can also get it here, right? I'm not telling you to be lazy. I don't want you to be lazy. I want your minds to be active and energetic and inquisitive and pursuing this. But I also don't want you to do busy work, right? Think about how you need to apply this to what you're doing. Understand where it comes from. It's just like your multiplication tables, right? Once you have mastered and you know your multiplication tables, then you can go forward and use your calculator when you've got really big numbers to use. Okay? When you're doing this, you can understand where the values come from. But when you're in a situation where you've got 20 problems you've got to solve, you don't have to do this for each single one of them. Use your calculator. That's what I'm getting at. So this is where the numbers come from. This is where the values derive from. It's from this here. But this is really, like I said, a cool tool to help you visualize all of that. And this will help you. This tool is great. Like I said, it's geogebra.org. You can just Google unit circle and click on the GeoGebra link and it will take you here. And this will help you with a lot of what we're doing with these vectors. This is 1 unit long, so you do have to extrapolate some information for the most part. So if you know your hypotenuse length, let's say your hypotenuse is 5, you can pretty much multiply everything here by 5 because that's the scale factor. So understanding scale factor helps you to extrapolate this data as well. So for instance, if the hypotenuse was 5, then that means that, let me get my calculator here, that the length of this leg, if the hypotenuse of this triangle was 5, then the length of this leg would be 5 times 0.78, 3.9 long. Does that make sense? All right, and usually what we understand about that is, if I have this in the right location, this should be 4. It should multiply to be 4. So what this might be is a rounded version of that. if I have this in the right spot. So anyway, my point is you can extrapolate some information here. You can use this to find the degree, you know, to help you out there. Use it as you need it for calculating some of this stuff, so you don't have to make so many, use up so much paper making so many notes. Or you can use this to help you find what it is that you need to draw, so that then you can put it in your notes without making a bunch of mistakes and having to erase and start over. You can figure it out on here, see it, and then make that quick sketch in your notes with all of this stuff already filled out for you. Okay? So I just wanted to show you this tool to help you figure out unit circle, to also show you how you can go a little bit faster, but also to illustrate for us how it works when we have a vector on an axis, and how those values are calculated, where they come from. Now that you know all of that, please go ahead and use your calculator just to go ahead and do the calculations in a very succinct way. Now, I do want to make one more point. And that point is that when these vectors are lying on the x and the y axis, we call those quadrantal angles. Okay? That's what they're called when they lie on the axis. Those vectors are laying on the axis there. Those are called quadrantal angles, and they are 0 degrees, 180 degrees, 90 degrees, 270 degrees in no specific order. These are the y's and these are the x's. Notice we don't have a 360 degree quadrantal angle. That is the same as the 0 degree because they overlap. They start and end in exactly the same place. So we have a 359 degree angle and then a 0 degree angle. That is the way it works. All right, so let's do a couple practice problems using what we have learned. Let's move up here to where it's blank so we can do some scribble scrabble. We might refer back to that drawing just for the sake of visualization. So let's start with example 29.1. And if I confused you at all, I apologize. We can talk about it further, or you can message me for some more reference information to help you figure that out. We are going to find 3 times the tan of 180 degrees. Okay, so like we said, 180 is going to be right here. It's laying right on top. So that means the tan of that is TOA, which is opposite over adjacent. So the tan of 180 is going to equal opposite is going to be 0, and the adjacent is a -1, right? So that's what we'll put up here. 3 times the tan of 180. So that's going to equal 3 times 0 over -1. Well, that's going to be 0. So 3 times 0, this is equal to 0. That's our answer. Could I have not just done this? 3 parenthesis 180 tan parenthesis equal 0. Same answer, right? Same thing we got here. Is it cool to know where it comes from? Yes. Is it does it help clarify some things in how the calculator solves? Yes. Is it absolutely necessary for the rest of your life? Maybe not. But now you know where it comes from. So let's do another one. Let's do 29.2. We only have 3 of these. So 29.2. It says we need to find, there's two of these, so 4 times the sine of 270 degrees and 3 times the tan of 270 degrees. All right, so let's look back at our reference. So the sine of 270, so 270 is going to be this one right here. This is the 270 mark. That's 270 degrees. So if we're looking for the sine of 270, then that is the opposite over the hypotenuse. So the opposite over the hypotenuse. So that's going to be -1 over 1. So that means the sine of 270 is equal to a -1. So we come back up here and we say 4 times the sine of 270 degrees is equal to 4 times a -1, which equals a -4. So we could do that on our calculator just as easy and say 4, open parenthesis, 270 sine, close parenthesis, equals, hold on, I'm hitting a button somewhere that I don't need to. So 4 times 270 sine equals -4. There's my answer. Okay? So you got to remember to put in this one on the computer, you got to remember to put the multiplication sign in there. So -4 is the right answer. So the tan of 270, that's the next one we have to figure out. So that was going to be 3 times the tan of 270 would equal 3 times something. So let's go look and see what the tan of 270 is. So the tan that is of 270, that's the opposite over the adjacent. Well, the adjacent is 0. The opposite is -1. So the tan of 270 is going to equal the opposite, -1, over 0. Oh, well, if it's over 0, guess what? That's undefined. Right? So we can't solve this one. If this is undefined, then the answer is undefined. We cannot solve for 3 times the tan of 270. Can't do it. So let's see what the calculator says. Let's clear this up and say 3 times, and that is the tangent of 270. So 270 tan, it tells us right away it's not a number. So we can't even do that. We cannot do that. It's going to say not a number every single time. So that's kind of cool that the calculator agrees with us. So 29.3, here's our last one. So we have an evaluation to make here, and it is the sine of -135 degrees plus 3 times the square root times of 2 times the cosine of 180 degrees. So I don't know why in the world they want to give us something that difficult. So what we would have to do is go to look at this and evaluate and say, that is the difference between 180 and 45. So that is going to be, let me just draw this quick sketch. Here is our quadrant map, and this is going to be 90. 135 is going to be right here, and that just happens to be a 45, 45. All right, so 45 degrees right here. Triangle. So we need our reference for that, and I'm just going to put it right on here. So this is going to be 1 and 1, and this is the square root of 2. Now remember, this is going to be a negative because it's on the negative side of the quadrant. So that is how we would end up putting that there. So now we can find the sine of -135, because that would be so, right? And then cosine would be ka. So we need both of those for this problem. So that'd be opposite over the hypotenuse for this sine. So the opposite side is 1. The hypotenuse is the square root of 2. So that is going to be the negative 45-degree angle. Oh, I did that wrong. I am so sorry. Let me start over. I read that entirely wrong. This is the negative 135. Don't let that trip you up like it just did me. So the negative 135, that means we measure this way. So we'll start here and go 90 and then all the way to 135 here. So this is where it goes to. I was looking at the answer going, why in the world is it like that? Now it makes sense. This is negative 135 from here to here. So that puts the vector there, which means that this is our 45 here, which makes this a negative 1, and this is a negative 1, and this is still a positive square root of 2 for the hypotenuse. Okay, now I can answer this question the right way. Let me put so, if I can put so, and ka back up here because we're going to need ka as well for the next part. So for so, that's opposite over hypotenuse. So the sine of negative 135 goes here. I'm not going to write that. I'm just going to put the answer. The sine of negative 135, that's going to be the opposite over hypotenuse. So that is going to be negative 1. This is my opposite, and this is my hypotenuse, over the square root of 2. That is all of that right there. Plus 3 times the square root of 2 times. Now I got to find the cosine of 180 degrees. So I'm going to just go back down here. I've already figured that out. The cosine of 180 is negative 1 over 1, which is equal to a negative 1. So 3 times the square root of negative 2 is going to be times the cosine of 180, which is a negative 1. I can double check that on my calculator by typing in 180 cosine negative 1. Okay, so I got that right. So now we have to resolve this because we know we can't have a radical symbol in the denominator. So we multiply the top and the bottom by the square root of 2. So I get a negative 1 times the square root of 2 over 2 plus negative, well actually that becomes a minus, doesn't it? Because it's times a negative 1. So minus 3 times the square root of 2 over 1. Right? I can just turn that into a fraction like that because it's a whole number. But I need it to have a common denominator so I can combine these. So I'm going to multiply this times 2 over 2. So that becomes negative 1 times the square root of 2 over 2. And then negative 3 times 2, that's going to be a negative 6 times the square root of 2 over 2. Now I can combine these and I end up with a negative 7 times the square root of 2 over 2. And that would be my final response. Cool beans? Not super hard, not really, when we stop and break it down. This negative threw me for a loop for just a second. I forgot that I have to go the other direction when it says the negative degree. So don't forget about that whenever you're doing these problems. And that's the last problem I have for lesson 29. And that's the end of lesson 29. Thank the Lord. I will see you in lesson 30.